Uranus, the seventh planet from the Sun, is an oddball. Unlike its planetary siblings, Uranus spins on its side. Imagine a top spinning not upright but tipped over. That's Uranus. Its axis of rotation is tilted at a dramatic 98 degrees. This peculiar tilt makes Uranus unique in our solar system. It's a cosmic mystery that has baffled astronomers for centuries. Why is Uranus tilted? The answer lies in the chaotic early days of our solar system. The discovery of Uranus's tilt was a pivotal moment in astronomy. In 1781, William Herschel, a British astronomer, stumbled upon this icy giant. He initially mistook it for a comet, but further observations revealed its true nature, a planet but one behaving strangely. As astronomers studied Uranus, they noticed its unusual motion. Its rings and moons weren't orbiting in the same plane as other planets. This led to the realization that Uranus itself was tilted. But why? Early theories struggled to explain this phenomenon. Some astronomers proposed that Uranus might have a large, unseen moon. In the late 20th century, a new theory emerged, the giant impact hypothesis. This theory proposed that Uranus's tilt was the result of a collision with a large celestial object, perhaps a protoplanet or a massive asteroid. This impact, according to the theory, occurred billions of years ago, during the early stages of solar system formation. The impact scenario offered a compelling explanation for Uranus's extreme tilt. A collision of such magnitude could have easily disrupted the planet's rotation, knocking it on its side. The theory also accounted for other unusual features of Uranus, such as its thin rings and its collection of irregular moons. The collision theory gained traction as scientists gathered more evidence. Computer simulations showed that a giant impact could indeed tilt a planet like Uranus. These simulations provided a visual representation of the cataclysmic event, showing how the impactor's momentum could transfer to Uranus, altering its spin. While the collision theory was compelling, it needed more than just simulations. Scientists needed concrete evidence, something tangible, to solidify the theory. The search for evidence led scientists to study Uranus's rings and moons. These celestial bodies, they believed, held clues to the planet's tumultuous past. The rings, composed of ice and dust, were thought to be remnants of the impact. The irregular moons with their chaotic orbits were also suspected to be debris from the collision. Further analysis of the rings and moons revealed intriguing patterns. The composition of the rings matched what scientists expected from a shattered icy body. The irregular moons with their tilted and eccentric orbits pointed towards a violent disruption of Uranus's original moon system. These findings provided tangible evidence for the collision theory. The rings and moons of Uranus weren't just orbiting companions, they were remnants of a cosmic catastrophe. They were the scattered pieces of a giant impact that forever changed the face of Uranus. Computer simulations played a crucial role in solidifying the giant impact theory. Scientists created sophisticated models of Uranus, replicating its size, mass, and composition. Then, they introduced a virtual impactor, a massive object representing the hypothetical collider. These simulations allowed scientists to experiment with different impact scenarios. They varied the impactor's size, speed, and angle of impact. By running countless simulations, they could observe how different impact parameters affected Uranus's tilt and other characteristics. The results of these simulations were striking. They showed that a single, giant impact could indeed tilt Uranus to its observed angle. Moreover, the simulations reproduced other features of Uranus, such as the thinness of its rings and the irregular orbits of its outer moons. These simulations weren't just visual representations, they were based on fundamental laws of physics. They incorporated gravity, momentum, and the behavior of matter under extreme conditions. The simulations, therefore, provided a robust scientific framework for understanding Uranus's tumultuous past. Uranus's tilt isn't its only peculiarity. The planet possesses a unique set of features that set it apart from other gas giants in our solar system. Its rings, while faint and thin, exhibit intricate structures and compositions. Its moons, both regular and irregular, offer a glimpse into the planet's gravitational dance. Uranus's magnetic field is another oddity. Unlike Earth's magnetic field, which emanates from the poles, Uranus's magnetic field is off-center and tilted. This unusual magnetic field is likely a consequence of the giant impact, which disrupted the planet's internal structure. These unique features of Uranus provide further evidence for the collision theory. They are not isolated anomalies but rather interconnected pieces of a larger puzzle. The tilt, the rings, the moons, and the magnetic field all point towards a shared history, a history marked by a violent cosmic encounter. Understanding Uranus's unique features is not just about satisfying curiosity. It has broader implications for our understanding of planetary formation and evolution. The study of Uranus's tilt has profound implications for our understanding of planetary formation. It challenges the traditional view of a peaceful and orderly solar system. Instead, it paints a picture of a chaotic and violent past, where collisions and disruptions were commonplace. The giant impact theory suggests that such collisions were crucial in shaping the architecture of our solar system. Planets didn't just form in isolation, they interacted with each other, sometimes violently. These interactions over billions of years sculpted the solar system we see today. Uranus's tilt serves as a reminder that planetary systems are not static, unchanging entities. They are dynamic, evolving systems, constantly influenced by internal and external forces. Collisions, while rare, are a part of this evolution, a testament to the dynamic nature of our cosmic neighborhood. The lessons learned from Uranus can be applied to other planetary systems, both within our solar system and beyond. By studying the aftermath of a giant impact, we gain insights into the processes that shape planets and their environments. These insights are crucial for understanding the diversity and evolution of planetary systems throughout the cosmos. While the giant impact theory is widely accepted, there are still unanswered questions about Uranus's past. Future research aims to address these questions, using more advanced telescopes, spacecraft missions, and computer simulations. One key area of research is the precise nature of the impactor. What was it made of? What was its size and velocity? Answering these questions will provide a more detailed picture of the collision and its consequences. Another area of focus is the long-term evolution of Uranus after the impact. How did its atmosphere and interior respond to the collision? How did its moons and rings evolve over time? These questions require sophisticated models and observations to unravel. Future research on Uranus will not only enhance our understanding of this icy giant but also shed light on broader questions about planetary formation and evolution. Uranus, with its unique tilt and enigmatic features, holds the key to unlocking secrets of the solar system and beyond. Uranus, the sideways planet, is a testament to the chaotic nature of our solar system's past. Its dramatic tilt, a consequence of a giant impact billions of years ago, has shaped our understanding of planetary formation and evolution. It reminds us that planetary systems are dynamic, ever-changing entities, subject to collisions and disruptions. The study of Uranus's tilt has led to the development of the giant impact theory, a cornerstone of modern planetary science. This theory explains not only Uranus's unusual orientation but also its unique set of features, including its thin rings, its irregular moons, and its off-center magnetic field. Uranus, therefore, serves as a case study, a cosmic laboratory for understanding the processes that shape planets and their environments. Its mysteries continue to intrigue and inspire, driving future research and expanding our knowledge of the solar system and beyond. Uranus, with its tilted axis and enigmatic features, is a key to unlocking the secrets of the cosmos. It is a reminder that our solar system, far from being a static and orderly place, is a dynamic and ever-evolving system, shaped by collisions, interactions, and the relentless march of cosmic time.